Good day, everyone. In this video, I will discuss to you the fundamental theorem of arithmetic. Here, we will use the concept of the fundamental theorem of arithmetic. This involves the method of prime factorization. Then, we will determine the greatest common divisor, or GCD, and the least common multiple, or the LCM, of two integers. Now let's have here the fundamental theorem of arithmetic. Every positive integer different from 1 can be written uniquely as a product of primes. Now let's have here an example. Say we have here 10. 10 can be written as 2 times 5. So we have here the factors of 10, 2, and 5. Now notice here that 2 and 5 are all prime numbers. Now let's have here another example, say 12. So again, here we are going to find the prime factors of 12. Or we will write 12 as the product of primes. Now to get the prime factors of 12, we can have this method. Say we have here 12. Now the product of 12, we have 2 and 6, but 6 is not yet a prime number, whereas 2 here is a prime number. So since 6 is not yet a prime number, we will factor 6. We have 2 times 3. So the product of 6, we have 2 times 3. And notice here that all the factors here are prime numbers. We have 2 and 3. Hence, we can write 12 as the product of 2 times 2 times 3. Hence here, 12 is written as the product of primes. Now, another example is the number 18. So here, 18 is equal to 2 times 9. And here 2 is a prime number, where 9 is not yet a prime number. So we proceed. 9 is 3 times 3. Here we have here the product of prime numbers for 18. We have 2 times 3 times 3. That's it. Now note here that the unique representation of positive integer n as a product of primes can be written in several ways. First, we can write n, a positive integer n, as a product of primes. So here, P1, P2, P3 up to Pk. So where P sub k is a prime integer, where P sub I are not necessarily distinct. For I greater than or equal to 1, but less than or equal to k. Another here, by the way, we mean here P1 and P2 could be the same numbers, or P2 and P3 could be the same prime number. Follow? Now here, for another representation of a positive integer n, so we have here P1 raised to a sub 1. Here, another prime, P sub 2 raised to a sub 2 up to another prime here, P sub j raised to a sub j, where all the P sub I are distinct. So P1 is different from P2, and P1 is different from P3, and also P2 is different from P3. For I greater than or equal to 1, but less than or equal to j. So in general, or we have here the formal product, the positive integer can be written as this one. Actually, this is the Cartesian product of all primes p sub I raised to a sub I. Now, let's have an example. By the way, where all but finitely many of a sub i's are 0. Now, let's have here examples to illustrate the concepts in representing a positive integer. Now, for example, we have 12. Say, let's have here 12. So again, here 12 can be represented as the product of primes. We have 2 times 2 times 3. But also 12 can be represented as 2 squared. We have here this 1 for the representation of that times 3. So we do have here 2 representations of 12. Another one, we have, say, 18. So 18 can be written as the product of primes 2 times 3 times 3. Hence, this can also be represented as 2 times, we have here 3 times 3 can be written as 3 squared. Follow? And let's have another example, say 360. So 360 can be written as 2 times 2 times 2 times 3 times 3 times 5. And another representation for 360 is we have 2. So for this, we have 2 cubed times for this, we have 3 squared times 5. So as simple as that. Now let's proceed to finding or determining GCD of 2 integers using the prime factorization. So we will consider here 2 integers, a and b, with where a is written as the product of primes. So actually, we use the method prime factorization for this. Okay, we have this one where P1, P2, P3, up to Pn are distinct prime numbers. Okay, for example, let's consider here A be equal to, say, 36. So we can write 36 as the product of primes. We have this one in this way. We have, or let's have here first, 36 can be written as the product of primes. We have 2 times 2 times 3 times 3. So we can write 36 as 2 squared times 3 squared, okay? And then for B, say for example, B is 60. So 60 can be written as 2 times 2 times 3 times 5. Or we can write this as 2 squared times 3 times 5. Now here, using this representation for this one, we have the exponent A1, A2, A3 up to AN. Now here we can denote A1 equals 2. So here, let me have here A1 equals 2. Here, A2 equals 2. Now for this, we have B because we have the exponent for this integer. We have B1, B2, B3, and up to Bn. So this is our B1. This is equal to 2, the exponent of 2. Then for the exponent of 3, we label it as B sub 2, which is of course equal to 1. Note here the exponent is 1. Then here we have B3. which is equal to 1. Hello? Now take note, we have n. What is our n? N here is equal to, what is our n here? N. So here, n is equal to 3. We have here up to b sub 3. Now notice here our a sub 2, our a for a here, we have here a sub 2, up to a sub 2. Now we will be finding what is our a sub 3, because as you can see here, we have n. They should have the same, up to n, a sub n. Now, recall that in our basic mathematics, what number can we multiply to 36 so that the value of 36 will retain? What's that number? We use the property of what? The identity property. For identity property, it means if you multiply 1 to a number, the answer is that number. Say 1. So we multiply here the number which is equal to 1. And what is that number which is equal to 1? Where P here is 5. By the way, take note here that P1, we have here P1. You should have the same P1. P1 is 2. So as you can see, we have P1, 2. And then for P2, the second prime number is 3. So as you can see here. And then our P3 is, we have 5. Hence here, because we will write P3 raised to A3, right? We have P sub 3 raised to A sub 3. This is our missing here factor for 36. So we can write it as 5 raised to, what is the exponent? Where the value is just equal to 1. Of course, this is 5 raised to 0. Okay? So 5 raised to 0. This 5 raised to 0 is of course equal to 1. And if we multiply it to 36, still the value is retained. So we have 5 raised to 0. Hence our A3 here is 0. Hello? So let's have, now to find the GCD, by the way, this is the, we will use this equation in finding our GCD. So to find the GCD, we have this, of course, this notation. So for here, we have 36, then we have the GCD of 36 and 60. Now take note here, we have P1. So our P1 is 2. Then we have the minimum of, so A1, B1. So A1 here is 2. Then B1 is 2. So this 2 here is the exponent for a exponent here in the prime factors of 36. So we have 2. Here, exponent for B. So this is B1. This is A1, this is B1. Then we multiply it to P2. P2 here is 3. And the minimum of, we have this one and this one. So minimum of A2 is 2. And then B2 is 1. Times P3, we have 5 raised to the minimum of 0 for A. Then for B3, we have 1. Okay. So of course, to get the minimum, we'll be looking at the smallest number in the set. So we copy here the base 2. Then the minimum of 2 and 2 is of course 2. Times, we have here 3. And the minimum of 2 and 1 is 1. Times 5. Minimum of 0 and 1 is 0. This is 4 times 3. Of course, 5 raised to 0 is 1. Hence, the GCD of 36 and 60 is equal to 12. Follow? Now let's have here another example. We are to find the GCD of this integer here. This integer is written as the product of primes, and another integer that is written as the product of primes. Here we let A be equal to this. And for our B, we have 2 squared times 3 squared times 5 cubed. Now take note here, P1, here P1 is 2, then P2 is 3, and P3 is 5. And we also have here, let us have P4 be 7, because we have a prime 7 here in A, and we have 5 in B. Hence, we can rewrite A and B as this one. So let's have here 2 cubed times 3 times 5 squared times 7. And this is 2 squared times 3 squared times 5 cubed. And then we can include 7 in B, but the exponent is 0. Follow? So we have now 7 as our P4. So we have P1, P2, P3, up to P4. Hence, we can have the GCD of A and B as, for P1, we have 2, the minimum of the exponents of here. So the exponent of 2 here in A is 3. And then our B1 is this one, so 2. Times P2 here is 3 raised to the minimum of the next. We have here 1 and then here 2. Minimum of 1 and 2. Times we have 5 raised to the minimum of, this is our A3. A3 is 2 and B3 is 3. Times 7 raised to the minimum of, this is A4. A4 is 1 and B4 is 0. Now let's get the minimum. So we have 2. Minimum is 2 times 3 raised to minimum is 1 times 5 raised to 2 times 7. Of course, the minimum here is 0. Okay. So let's answer. We have here, this is 4 times 3 times 25 times this is 1. Hence, the GCD of A and B is equal to 300. So you can check it. This is 300, or times 3 times 25. Now let's have another example. Let's consider this one. We are to look for the GCD of 120 and 252. Now we let A be equal to 120 and B be equal to 252. So we will write each integer as the product of primes. So in this way, this is, for 120, we have 2 times 2 times 2 times 3 times 5, or we can write it as 2 cubed times 3 times 5. Now for 252, we have 2 times 2 times 3 times 3 times 7. Or we can write it as 2 squared times 3 squared times 7. Okay? So to write that in this manner, because we have here P1, P2, P3, up to Pn, so we can write it this way. 2 cubed times 3 times 5 times 7 raised to 0, because we have 7 here in our B as a factor. So we write the factor 7 in A here, but raised to 0. In the same way, we have here for B, we have 2 squared times 3 squared times we have 5 raised to 0 times 7. Hello? Now we have here P1. So P1 here is 2. P2 is 3. We have here P1, P2. P3 is 5. And P7, P4 rather, is 7. So to find the GCD of 120 and 252, we use this one. So we have the GCD of 120 and 252 is, we have P1 is 2 raised to the minimum. Okay, we will answer it directly. Minimum of 2 and 3. So we have this one, 2 and 3 and 2. The minimum is 2 times 3 for P2. Minimum of 1 and 2 is 1 times 5. Take note here, we have the exponent here is 1. We have 0. Minimum is, of course, 0. Then times 7, minimum is 0. So we have here 4 times 3 times, of course, this is 1. Hence, the GCD of 120 and 252 is equal to 12. Follow? As simple as that. Now let's proceed to finding the LCM of two integers using also the prime factorization. Again, we let two integers, A and B, they are written in product of primes with this representation here. And to get the LCM, by the way, this is the symbol for LCM, we consider the maximum of its exponents. Wherein for our GCD, we considered minimum of their exponents. But here, we consider the maximum. Now, let's have an example here. We are to find these integers. So for these integers, we'll let this as our A. This is our B. Follow? Now, to find the LCM, we have this notation for the LCM. This is equal to, take note here, our P1 here is, P1 is 2, P2 is 3, we have this one, P3 is 5, and P4 is 7. Follow? So we have 2, 3, 5, and 7. So here, we are to look for the maximum. P1 is 2. We have the maximum of exponent of 2. We have 3 and 2. So maximum of 3 and 2 times another P prime. We have 3 raised to the maximum of, for the exponents of 3, we have 1 and 2. So 1, 2 times 5. So raised to the maximum of, for 5 exponents are 2 and 3. So we have 2 and 3. Times 7, the maximum of, okay, the exponent of 7 here is 1. And of course, we can multiply this integer by 7 raised to 0. So exponents 7 and 0. So we are to look for the maximum of 1 and 0. Hence, we have 2 raised to the maximum of 3 and 2 is 3 times 3 raised to maximum is 2 times 5 raised to, oh, by the way, the maximum is 3. So here, 3 times 7 raised to, its maximum is 1. Hence, we have here, this is 2 cubed is 8. So 8 times 3 squared is 9 times 5 cubed is 125 times 7. Okay, so the product is, you can use your calculator to get the product. We have 8 times 9 times 125 times 7 is equal to 63,000. So we have here the LCM of the given two integers, A and B. Follow? So let's have another example. Let's try to find the LCM of 120 and 252. So we let A be equal to 120 and B be equal to 252. Here, 120 can be written as 2 cubed times 3 times 5, whereas 252 can be written as 2 squared times 3 squared times 7. Now take note, we can also write this as 2 cubed times 3 times 5 times 7 raised to 0. Here we can write 2 cubed times 3 squared times 5 raised to 0 times 7. Hello? Hence, the LCM of 120 and 252 is equal to 2. So for our P1, we have 2 raised to the maximum of 3 and 2. So we have here, the maximum of 3 and 2 is 3. Times P3 here is 3 raised to the maximum of 1 and 2, we have 2. Times 5, maximum of 1 and 0 is 1. Times 7, and the maximum of 0 and 1 is 1. So we have here 8 times 9 times 5 times 7 is equal to, okay, let me use my calculator. 8 times 9 times 5 times 7. This is actually equal to 2,520, which is the LCM of 120 and 252. That's it. So we are done finding the GCD and LCM of two integers using the fundamental theorem of arithmetic. Now, thank you for watching and listening. God bless everyone.